Okay, so last time we talked about VQE, right? So we did a VQE simple example of the field and the spin. Yeah, and we use, for example, you can use two local and just one qubit, or you can use this efficient SU2 ansatz. So you can get it. Okay, these are described in this document. Yeah, you click. Okay, I'll click now. So we saw this two local previously, but I think for the programming, it's okay to refresh what you have seen before. There's a two local gate. If you're interested, you can check the documentation in more detail. This is a class, right? Qiskit.circuit.library. And these are the parameter, number of qubits, rotation block, entanglement block. What kind of entanglement? Do you have repetition? Skip unentangled qubits force, skip final rotation there, etc. There are a lot of parameter options. Okay. Yeah, more description. Like 4 is all-to-all connections. Linear is just the nearest neighbor. You can also reverse one layer where qubit I is entangled with qubit I. So for all even the second layer, okay, this is pairwise. Also circular. It's linear, but the last one, the first one would be entangled. Shiftive circular alternating. Yeah. The entanglement can be further specified using an entangler map, which is a list. So you can try this if you want to design some variation of ansatz. It is also, yeah. So this is an example of this. Let's show you how you use the entangler map. This is interesting example. So you can specify the entanglement map according to your device, right? Which qubit is connected to which qubit. There's an entanglement CNOT gate that you can apply, and then this would be according to the structure. Entanglement map. So this entanglement map is specified here. The entanglement here. Okay. There's also efficient SU2. Number of qubits, SU gate, entanglement, repetition, very similar to the other one. This is 3 qubit, you have repetition. 4 qubit SU2 gate, you specify SU2 gate, X, Y. This is entanglement. It's circular. So you see that This one, it's linear up to the last one and the first one also connected. The class is pending deprecation as of Qiskit 1.3 will be marked deprecated. So this evolve quickly, so you have to see that. Okay. So the summary of VQE is this diagram. So you have some Hamiltonian, you want to minimize energy. It can be some of a few terms. For example, our single qubit case. And what you do is you prepare your quantum state and you measure the observable. For example, H1, H2, etc. And you add them together according to the weight. Then you use your classical computer to check what will be the next parameter you want to try. Of course, you can try a few one and then you select what. So, and then you repeat this cycle until the energy is minimized. Okay, so we can talk about a few applications later, but maybe not at this stage. There's some application like MaxCut, even machine learning, quantum chemistry. So in here, it's important to know how you write your operator, right? So we use mostly spin. So Pauli operator is the most important one. So let's look at the operator overview. We have some notebook. If we have time, today we may talk about Transpile. Let's see, operator, Pauli operator. You can download from Brightspace. Share this. We also have another, I think that next homework I plan is quantum error correction. But it'll be a week from now. Okay, so let's see. I uploaded. This is just to show you how to write the operator. So you will import just a quantum info operator. We've seen the operator earlier, much earlier. Pauli, SparsePauliOp. Yeah, so this class represents the linear combination of the strings. Okay, it has a few ways to initialize. So one example here is you have SparsePauli from a list. You have ZX and 1, 4, 1, 0. This indicate Z is at 1, but in Qiskit you count backward. Okay, so the 0, 1, 2, 3, 4, 4 represent the x here. Coefficient is 1. Y, 0, 3, so you need to count 0, 1, 2, 3. Okay, 4. So I guess it takes the maximum label and to specify the string of the operator. Maybe not. It's specified by this number of qubit. You can try. If I don't specify number of qubit, it probably would show error. Or see if it's smart enough. Let's see if I take this out. See if it can. Okay, so you need to, yeah, you need to specify number of qubit, which is reasonable. Okay, this is nice feature. It can support arithmetic operation. Okay, let's see what it's doing. Let me show you. This is downloaded from the documentation. This I have the link if you want. This is basically downloaded from here. Okay. But sometimes I try a few different things and maybe there in the notebook. So you can have these arithmetic. So now you define another operator xz. This is 0, 1, 4. So you need to write. Okay, you need to write like 0 is x, 1 is x, 2 is identity, 3 is identity, 4 is z. And it's 1 plus 2j. J is square root minus 1. And the next one, this is 1, 2. So 0 is identity, 1 is z, 2 is z, 3 identity, 4 identity, and this is minus 1 plus j. Okay. Okay, then it has the operation. So you add the two. Basically, since they're all different, so basically just the list of the 4, x, I, z, I, y, and then these two, right? And you can 2 times, okay, 2 times the operator, really just multiply the coefficient by 2. This operator 1 add operator 2, operator multiplication. Okay. But we need to make sure which one times which one. So which one apply first? This is operator. So let's check. We can check. Let me see if I can annotate it. Let me try annotate. So you have operator 1 is xiizi plus -1 is j iy y. Operator 2 is, as we wrote there, 1 plus 2j ziix x plus -1 plus j I z z j. So if it's operator 1, okay, this is the statement is operator 1 at operator 2. But I don't know which one first. So that is do the operator 1 times operator 2, right? So assume 2 is applied first, then I would have this one times that. 1 plus 2j. Identity times x is still x. Z times x will be iy. So I have an I here. Okay, let me just put it here. And identity times identity, still identity. Identity times identity, identity. X times z. X times z is minus iy. Okay, so that cancel that one. Okay, and I have other terms. Let's see, we can compare yiiyx, yiiyx, the coefficient is 1. This cancel out, it's 1 plus 2j. Okay. But since these two commute, so it doesn't tell us exactly which order. This one, -1 plus j, a lot of identity, and oh, these two also commute. So x times identity, this is xi z I because the 2z cancel. So this won't allow us to infer any. Yeah, so this is here. Xiz here, coefficient. Okay, and we do this times that. Minus I plus j, 1 plus 2j. Identity times z, y times I times I times x, y times x is minus iz. Okay, at least this one will tell you which is which. Okay. Then you also have this last term, minus I plus 1 square I y z zy. Okay, this is confused. So this is the one that will tell us whether the coefficient okay, this would be I should write j. So z y I x z. What is the coefficient? Is this one this? Or no? This is this the coefficient? This is this coefficient or not? Right. So okay, that just multiply by this. So this is a -1, and this is -2, so it's -3, right? And the cross term -2j plus j, so is -j, but you also have -j, so when you multiply, it's 3j -1. Okay. So we get a negative sign. So this is actually operator 2 times operator 1. Because operator 1 apply first, and then operator 2. This is by calculation. Okay. But usually you can refer to the documentation as to what is what. Okay. Let's put it here. According to our calculation. Operator 2, the operator. Okay. So we know when you write, you know what is what. Okay. So just okay. And this is the other class is Pauli. So sparse Pauli is designed to deal with the case you may have a lot of identity. So that's why it's sparse. Pauli represents a single Pauli string with optional confusion. Okay. Single. Okay, single. We can choose from I, X, Y, Z. Okay, so this, that. Okay. This I is the coefficient I, and this I is the operator I. So don't get confused. The two code cell demonstrate, okay. So now we try some use. Dimension of this operator 1. What is this dimension? And that's, it's two qubit operator. It's dimension 4. What's the phase? Phase of I, boy, three properties representing, I'm not sure what is the phase of this is.
Why is the dimension in 2 code?
Say that again.
It's 4, 4, right? What is it?
Oh, 4 by 4.
Oh, okay.
Phase of I, X, X. Let me see. Why is it using 3? We could try other thing and see. We can figure out by defining operator. If we define this
Phase
exponent, let's say if we say +1, and the phase zero, okay, and -1, 2, what? Okay, so let's just keep a record. +1 will give you 0. -1 will give 2. It's probably the I, minus I is 1. And I is 3. So probably using minus I to some power. Yeah, that's why you can figure it out, right? So where is the documentation? Yeah, so you can always look at the documentation, but by playing this, you also figure out this by yourself, right? Yeah, the face. Yeah, I don't know why the face using the integer. Yeah, so it's a design of the programmer, and some may be very intuitive to you, but some may not. Like this is not intuitive to me. Why you want to use minus I, right? You don't want to use I. So there's when you're designing this also on your own, you have the choice you have to make. You have to break the symmetry. Sometimes you choose left or right. Okay. But these operators will be things that we use to design the Hamiltonian and things, or translate the fermion operator into spin operator, and then you can calculate quantum chemistry. Okay, operator class. We saw this operator class. Okay, so you can initialize by giving a numpy array. So this, let's see, we can, I remember we can, is it too LaTeX? If we can, okay, remember we were printing that and using LaTeX. Let's see if that has, in our earlier, yeah, so it's good to have the notebook organized. And so when you forget, you can always go back. Maybe it's here, summary of. We can print a LaTeX, draw LaTeX, draw LaTeX. Hopefully this one. Right, okay. So you can draw in a nicer looking. Okay, operator, object stored under the matrix, input, output, dimension. Okay. So you want to access the numpy array, you will call data. So also there's dimension, operator dimension. It's already, it's similar to previous Pauli. Here we have the dimension. But here it's using so there shouldn't be a S. Okay, dimensions. Right, this should be die. It is 4x4. Operator. So you can also initialize the dimension to random dimension. Output dimension. So this is 2 times 1 times 2 to 2 times 2. So it's 2 times 4 matrix. And input is the right one. So it's 2 times 2. So you're using 2, 2, and output is 2. Representing that the input is 2 qubit, output is 1 qubit. If the input is not divisible into qubit subsystem, right? So this is saying here, it will be stored as a single qubit operator. For example, it's actually not a qubit, single 6x6 matrix. Okay, input and output. So this is more general than Pauli. Okay. Yeah. You can also manually specify. So it's input, it says input dimension 4. Then when you output, it's the 4 and 2. But let's see if we don't enforce, then it should be, yeah, it's already up there. But if we don't enforce, it will be 2 2. So if you don't enforce, it will be 2 2, as we saw earlier. Okay, specify the qubit and qubit. Qubit is 2 dimension, qubit 3. So the 6 can be decomposed into 2 times 3. So this is how you manage that. Of course, the moment the device does not have qubit, that you can operate. You can also extract the input or output dimension of subset subsystem using input dimension. Okay, so that's 0. This is operator we define here. Yeah. This is 2 and this is 3. Yeah. Okay. This is from the documentation. Another one that I also downloaded is the operator class. That was the operator overview, and it's also operator class, and see if, how much overlap they have. If overlap too much, we don't need to go through. Here they also gate. So that's we have seen the gate before. So input quantum circuit. This is a control Z gate, X gate, X gate. Okay, so import operator Pauli process fidelity. So there's no SparsePauliOp imported at this point. Okay, just using Pauli operator. So we define XX operator. Okay, you have to say operator Pauli X, and give you the create operator for gate object. This is the control X gate. So if we want, we can draw this latex. It looks better. And it's different from we commonly see, right? We usually see it 1 1 and then 0 1 1 0, because this is the different order. What if we can somebody find how we, I think we could, let's say, I think we can say what would be the qubit to apply. But we need to know how to input. Is it just 1 0? We need to know maybe the control and target, something like that. Let's find out what is. I don't think this will be the correct one. But let's find out. We need to find out the CXK class, how to use it. CXK. I think you will do a lot of these kind of documentation lookup to see how it's used. How do we or you have to arguments. Okay, what would be the arguments and Q argument? Keyword argument. Control state. Label. Give it number control. Method. Inverse. This is a practice of documentation. Look at it. There is a multiple. We see MC multiple. Number control gate. Control state. Maybe it's afterwards. Once you define a gate and then you say what the gate is applied to. Remember we see these gates before. Wait, what? Maybe summary of the operation. So in the control, we just usual C the lowercase cx, we just say which one is which. But this is when we were applying to the circuit. This is elementary, but I don't know. In this notebook we have these multiple important. Maybe it's in the earlier and other one later on.
I think this is a constructor, right? Maybe put an integer here. I don't know. You have to just
String.
I think just like
Control state.
yeah in the initialization.
But a control state may indicate you could use 0 as a to stay with you 0, then you flip. Control state. Maybe we try that first. Okay, let's try that. Okay, so let's, where are we? Yeah. Okay, let's not change that. Let's say control state. Control state equal 0. Is that?
CTR.
So this will be controlled by 0. But I want to make it to the usual way of looking at. We'll need to change the order. Maybe. Let me just put this back. Doing anything. Well, it's a class. And we reverse. What are the options? We'll see the options. control state, condition bit, condition. This is different. But they should have number of control bits. This is single. The combination definition. I think we understand the control state. Label is just
If you go to the GitHub page, it says that it can be expressed as an integer or a string.
We'll just say encoding from string.
Yeah.
It doesn't specify.
a string.
It can be an integer or a string.
What is a parameter? What's
Things to control, right? But it's just like
control? You mean this control state?
yeah, but you can put string in it, but I don't know
0.
what kind of
Well, if we put 1, would be it could, yeah. This is saying that you could
about 0, 1, or is it multiple control?
No. Yeah. It's just the state that you want to have the action, right? And this is 0 or 1 is you can use integer instead of the string. Okay. Let's try to, if we can figure it out, that would be useful. But I suspect when we create the operator, then when we apply, we specify. Usually we will specify how you act. For example, let's see. We have quantum circuit. Okay. Let's see. We say operator 1 is this. QC quantum circuit. We have 2, right? And then we would QC. Okay, that's the Hadamard 0. And QC. Do we append OP? And then we specify 1, 0. Right. So I guess at that point, it does not care about which it has already a default assumption. But when you draw, when you draw, you can say this is the 0 and that's 1. Okay, you can decompose. So I guess you cannot really change that. Because it already have some implicit, it's already like 0, the 0, 1, the 0, 1 is the control, 1 is the target. And when you apply to the circuit, you can say the order, and then they map the order. Yeah. Yeah, but to see that get flipped, we have to use so for example, we have to say, okay, let's not use 0. Let's use this. And then let's not do this. Right, we append this, and then we can do the operator QC. Draw. Operator. Okay. So this will be the usual way we see the control line, but you can't directly change from here. We have to apply to a circuit, and then yeah, you could also have. Okay, we're just playing with these circuit in more detail. Operator, combine with the operator. Here you can say controls state is 0. Right, so that means when it's 0 in our usual ordering, the 0 it will flip. Okay. Yeah. Okay. Yeah. So, and this is our X gate. Let's just use this RX gate. So rotation by the angle pi over 2. Okay. Now there's combination with circuit. So it's creating 10 qubit circuit and apply Hadamard 0. And from 1 to 10, it's doing these control that are so 1, so 0, 1, 1, 2, etc. And then they want to convert that to an operator. Let's first show the circuit. If I just show the circuit, right? And this is the operator. Okay. Yeah, use the operator in circuit. I just show you an example. So here is another example. You have Pauli XX. You have 2 qubit. You append this operator, but it's already assumed when you write XX, this is a 0 bit. This is the first bit, and you apply that. And but when you want to switch order, you only do it at the level of circuit. Okay, you do measure and draw. Okay. But it does not show it as X. So it will show this unitary. And you can actually give a name. Is it label or name? To label. What is the options? Operator. The label or name or something. Could be name. Oh no, he does not. Data dimension. It does not allow you to even give a name. Yeah, so there's no options for you to change to. So you will always show up as unitary. But which could be weird because if I create operator by applying by just specifying the matrix, if it's not unitary, it will show up a unitary. For example, not here. Let's close this. Right here, I could use this as I could use numpy. I could use numpy, but if I input something which is non-unitary, still show up. Let's just play with this. Okay, this is a fake. I'm going to just set this 0. Okay, I'll just change this to fake. Oh, it was operation. So it knows that. Let me see if I change it back. Oh, so it checked. Internally, it checked whether it's unitary or not. Okay, if I say 0.5, then it's not. Input image. So, okay, there is some checking mechanism for this. We don't know. I mean, we have to look up the documentation, to know what is the exact definition, or is there any checking mechanism, etc. So you can know it by reading the documentation, but I guess nobody will look through the documentation, and then after that you do the programming. So you probably try and find an example that people provided, and you play with that. And when you need to have deeper looking, you go back. Okay. Yeah. So now we know, right? But playing with these by modifying the code to see, okay, does this work or not? Then you have, and you become more knowledgeable about what you can do. So yeah, we know this is just a pen. Okay. You can also combine operator, tensor product, A tensor B. Okay, so they explain this. Let's see. They explain here. Two operator can be A direct B operator tensor, not both be a single qubit. A dot tensor B will have the subsystem be 0 and B on 1. Okay. A tensor B, B will be on the 0 system, A will be on 1. That's a default. You need to look up the documentation to know how it was designed. Tensor expand. It's like a tensor product, but in the reverse order. Two operate A and B, and you have, okay. Okay, it's called tensor expansion, but it's a tensor product, but the reverse order. Okay. Okay. Composition. A dot compose B, return operator A and then B. A then compose B. Okay. You can compose in the reverse order by applying B in front of A using the from keyword. Okay. So this will be doing B dot A. A compose B, but from true. So B is in the front. B dot A. So system composition. The previous compose required total output dimension of the first qubit A equal to the total input dimension of the compose B. Okay. You can this is allow you to compose a smaller operator with selection of subsystem and a larger operator using keywords of compose with or without from. Okay, in this case, in the compose must match. Okay. Yeah. For example, to compose a 2-qubit gate with a 3-qubit operator, compose XZ with a 3-qubit identity operator. So this is identity. So A by A matrix, XZ operator, and then you can compose. So apply in our compose, right? Compose A compose B would be A first and B second. So we need to remember the ordering. So this would be operator, it's identity first and then do the XZ. But the XZ would apply to XZ. So this will be applied to 0. This will probably be the second qubit. Yeah. Yeah, so there are a lot of detail, but you never know when you need this operation. Compose YZ in front of the previous operator. Okay. So operator compose YZ in front. So YZ will apply first and then followed by the identity. Linear combinations. Okay, you can really just write multiplication and addition, subtraction as usual. So we'll give you the linear combination operator. And once you do that, it's likely it's not unitary. So you can check if the operator is unitary. Okay. So this operator identity here, you explicitly convert. So basically you explicitly convert these. And you can compose with a matrix. If the second is not already operator, it implicitly will convert. This is just the convenience, I guess. It's also probably from a programming perspective, it's just lazy. I don't want to write another operator, so I just define my operation to implicit converter. Okay. Compare operator. Are they the same? Okay. X operator, S gate is this times that. If you have a phase, it's not the same. Okay. Process fidelity, you can use the process fidelity function. Quantum, this is theoretically quantum for how close to quantum channel are to each other. In this case, unitary, it depends on it. Does not depend on the global phase. Yeah, so for example, yeah, here define a gate, X gate, and here it define a phase times the X gate, and the process fidelity from this quantum info would treat them as the same. So then you have to see what exactly is process fidelity is defined. And we would go to the documentation. We go to documentation. Okay, it's shown here. The process fidelity, yeah, is shown here. So it's you apply one of the, this will be a channel, apply to a state, and then you reverse that, right? You reverse that. And you measure how good respect to the original size state, and you integrate it over all the state.
That's with respect to.
You need to have a measure.
Okay.
Yeah, you need to have a measure. Yeah, it's a harmless.
Practically, use how measure.
Yeah, it depends. Like if you have usually you have these T design, and you can just do it with respect to a few yeah, Pauli, at least 2 design. I think it's 2. Okay. Okay. Let's see if I have too many of the documentation. This is the next topic, is the transpilation, which is related to what we mentioned earlier. In this, let me see the slide. So maybe let me go to the slide first. Okay, so following what I planned, so we talk about the operator, and then this actually would be combined to here, the VQE, right? So you would define your Hamiltonian in terms of the operator. So if there is a project, you need to write some operator according to some of the optimization costs, and then you need to write in terms of these operators. And that's what we use using Pauli or SparsePauliOp. And now we go to a different subject, which is transpilation. Let me see, let me use the slide. Okay. We've seen this, right? So we've seen this. This is an example code here. So if you don't want to do this manually by yourself, what you do is just say transpile preset manager import, generate preset manager. Okay, so what you do is basically this code here. You just say pass manager generate preset manager. This is the optimization level. We'll talk about optimization level next. But, and then you specify which machine, with back end, you go to back end, and you just transpile the circuit. You say pass manager.run circuit. Run is to run this pass manager, and you get a transpile circuit, right? So this circuit can be abstract, and the transpile one will be transpiled according to the basis gate set of this back end. For example, this back end could be Sherbrooke, could be Brussels, could be other machine, Torino, etc. in the real IBM backend. Yeah. So the purpose is to translate the circuit into a form that can be efficiently executed on a quantum device. And sometimes you want to allow the gate to combine. So there will be a different optimization level. So if you know X times Z or something, they can combine to a Y or something. Or more complicated, you have a C naught, another C naught. If you can optimize by become identity. So if you set optimization level 0, then it will not do these kind of. Okay, so yeah, so this transpile your circuit with reasonable default setting. Yeah, this is a preset. So most of the time you would just try this. Then what you can do is also print out the circuit depth, right? We saw this how you just say circuit dot depth, and then you see what is the depth, and then you can use other way continue the if you want to continue these transpilation options and see. Okay, maybe you just say, okay, I want to do optimization level 2 and see if the depth is reduced. And this is the code. the whole code, example code. Yeah. Okay. So here is really the aim is to run them on this machine, IBM version. So in doing that, you also need to use a Qiskit runtime service in order to access the backend. So you choose your device backend. It could be a simulator. Create a preset stage path manager. That's this path manager here. From this preset path manager. And run this. Okay. Yeah, optimize it. So just a few summary of the optimization level. And also like to disable. Okay, yeah. This is something I have not explored much. Like disable, yeah, never use a skip transpilation. So optimization level 0, no optimization. Used for hardware characterization. Like you really want to see the gate as applied. You don't want it to change. So you would try, for example, you want to estimate the gate noise. You don't want it to combine because I might apply x 6 times. The error may be bigger, and if I optimize the identity, so that's not the real hardware property, right? So this will be usually for hardware characterization or debugging, or you are doing scientific study on the hardware. Basis translations, layout as specified. Layout is the which qubit map to which qubit. Routing, this will be the swap. If you say I want to do the CNAP between 0 and 10, but they are not directly connected, you will swap. Okay, here it's called routing, and they will probably try find this stochastic. Okay, optimization level 1 has some light optimization. Do some layout trivial to this VF2, and this several layout if routing is required. So this will be explored in more detail in that lab 1. So we'll ask people which lab they want to cover, but this will be covered in lab 1. Routing, 1 qubit gate optimization, like combining error suppression. Okay, level 2 after medium optimization. So let me not go into too much detail. Heuristic so for example, heuristic optimize with greater search depth and trials of optimization function. Trivial layout is not used. There's no attempt to use the same physical and virtual qubit. Level 3 is high optimization and use more sophisticated algorithm decomposition, etc. Yeah. There's also documentation. And that means I've downloaded the code. This documentation. This code here, I downloaded. Yeah. The notebook that I downloaded. So I explained here. Okay, so we're going to look at this code. Maybe from here so I can run this. Yeah, should be very quick. Okay. Wait. Oh, I think I probably overwrite the file. So the one that I uploaded probably is not correct. this is the same. I think it could be overwrite. So yeah, so I would update that. So then let's look at here directly. Yeah. Okay. Yeah, unfortunately, I might have tried something on my own, but these get erased because it was copying and then yeah. Anyway, so let's look at the original code. So from the documentation. So yeah, the package on the circuit, unitary gate, operator, random unitary. So random unitary, is this the one that this is set up? Is this the right? Yeah, this is the right. Okay. This is the circuit. Random unitary, so 4x4, so there's 2-qubit gate. It's randomly generated. And then you use random unitary gate to make it a gate. And you create a circuit and apply these append gate. Yeah, usually when you create this, you would do append. And then range 2, only 2-qubit. And they do a swap. Okay. And they use a fake sharebook to import that you from the Qiskit IBM runtime fake provider, import fake sharebook. That's where your backend. And we said you say path manager equal to generate preset path managers. And then you tell it the optimization level, which backend, and you can specify a seed transpiler. If you fix the seed, next time it does anything, it will repeat the same thing. Then there's no randomness, it's fixed that. This is for you to debug. But if you want a different outcome, you can change the seed. Okay, so QCT1 exact, this is, okay, run this, and then draw this. Okay, this suppress, this, remember this idle wires equal to false is to suppress other qubit we didn't use. Otherwise, it will print a 127 qubit circuit. Okay, the transpile circuit has 6 of the 2-qubit ECR gate. If you look at the, we saw this earlier, different backend has different 2-qubit gate. And Sherbrooke is using the ECR gate, echo across resonance. And you repeat this for optimization level 1. This is 0. Okay. Yeah, unfortunately, I cannot run this and then show how many depth they have. So you do this, you use optimization level 1. You see they choose the same seed. Yeah, they choose the same seed. And I don't know, by looking at, maybe it looks like there are fewer gates, but I'm not sure. And the transpile circuit still has 6 ECR gate, number of single qubit gate have gate. So it reduced single qubit gate. Now you reduce the optimization level. This is as what I said. You can change this and play this, and you output this. Same result at optimization level 1. Increasing the level of does not always make a difference, right? Okay, repeat level 3. Now only 3 2-qubit gate. We obtain this result because of level 3. Qiskit try to resynthesize 2-qubit block of gates. And any 2-qubit gate can be implemented using MO3 ECR gate to get even fewer. If we set approximation degree to a value less than 1, allowing transpiler to make approximation that may introduce some error. Okay, so this is saying you can allow the optimization to be more efficient, but allow it to do some approximation degree 9.99. And only to exact A, but it's approximate circuit. Yeah, its effect differ from exact circuit. Yeah, so here you can calculate fidelity. Remember, we use the fidelity process fidelity. Oh, this is a different one. They directly, I guess. Yeah, they're not using the process, but you could use that process fidelity. Okay, this is exact one circuit, approximate one. They use this function trace to fidelity to qubit. Okay, so the exact. Yeah, so this would be comparing the one you created as operator and use NP dot to compute the inner product for the dagger times U, and then do the trace. Yeah. You can see the exact, of course, has to be the same. Approximate is 0.992. So sometimes maybe for application, approximation would be good enough because your real device would have errors. And this may allow you to shorten the depth. I think this is where at the regime you do approximation may get better results. Because if you have longer depth, the error actually make it worse. Yeah. But you don't know if you're running really large circuit, and if it's for short depth circuit, still okay. You can still calculate this fidelity. But if you for really large circuit, long depth, and it may not be efficient, even for classical computer to simulate. Okay. Okay, I'll download this again, and I'll update the book. Set optimization. Okay. Okay. I guess that's it for today. Any question? Yeah, it's a slightly I don't know, boring in the sense we are looking up documentation, but this is what programmer do very often. Unless you know that already very well, and then you already have that in your brain, but a lot of time we still need to look up. Like we still need to go back to a textbook. Okay, what is this formula? Yeah. And by going through that and then try to make modification of your code and you learn. Okay. And so homework 3 is now available. Work on it. Okay. So I'll see you on Wednesday.